All right, well then let's get started. Does anyone have any questions from any of the homeworks from last week's lecture or last Monday's lecture? Is today Wednesday? Today's Wednesday. Thank you. All right, well then I take it everybody is well familiar with how to add and analyze series and parallel resistors in a circuit. How many of you are familiar with Kirchhoff's rules? Well, you're getting there. You're close. That's one of them. How many rules does Kirchhoff have? No, there's two of them. What are they? Current law and the voltage law. Basically, paraphrasing, Kirchhoff's voltage law states that the sum of the voltage drops around any closed loop must equal zero. And Kirchhoff's current law states that the sum of the currents in any node must equal zero. In other words, if you've got three wires that come together, current comes in through one, comes into that node from one wire, and it leaves that node through two more wires, then the current coming in must equal the current leaving. Okay, that's probably the simplest way to state Kirchhoff's current law, is that the total current coming into any node must equal the total current leaving that node. Pretty simple statements of laws, and they should be pretty obvious or kind of intuitive. Conservation of energy, conservation of charge, however you want to look at it. Now, this won't always be true because eventually you're going to get to dealing with AC signals and circuits and resonance circuits, and when you start dealing with filters and resonances, then suddenly charge can accumulate in different places and hide out, and you end up with weird things going on like a Q rise in voltage or a Q rise in current. And just in case any of you don't realize this, when they talk about a Q rise in voltage in a resonant circuit, it may look kind of fantastical, like, oh wow, you got this little 3-volt battery, but it's generating this 15,000 volt potential out here. Well, I'm here to tell you that 15,000 volt potential, it may happen. They may call it imaginary numbers when you do the math. The voltage is real. And if you get a hold of it, it will knock you in the dirt. Okay? Point of that whole little diversion was simply to make that point, that there will come a point in your careers when you're working with other kinds of signals and resonance circuits and things that charge will still be conserved, but it won't necessarily obey Kirchhoff's law. It'll accumulate in places. And you can build it up, and it will manifest in different ways. But we're talking about DC or steady state currents and voltages, so resonances aren't going to apply. Whatever current, whatever charge goes in has to come out. Whatever voltage is applied around the loop, it has to sum up to zero. And these laws, though they seem kind of simple, they can actually be very handy when you start analyzing rather complicated circuits. Circuits that aren't necessarily intuitively obvious. In fact, some of them can get rather complex. We looked at things like this in the lab yesterday. We have a resistor, and then you have a couple of resistors here. Then you have more resistors down here. Okay, well, the first three were okay. You just add them together. That's pretty straightforward. But now you got some that are in parallel with these, and these are in series with those. Even here, even though it's starting to get a little more complicated, it's still pretty manageable once you look at it and realize, okay, well, these two become effectively one resistor. These become one resistor. So you have these two in parallel, which are in series with this one. You can still do the math pretty straightforward. Let's look at this problem in the book. And we'll learn that maybe they aren't always as straightforward. So let's start with a 30 ohm resistor. Here. Here with a 40 ohm resistor. Coming over to a 1 ohm resistor. Now let's put a voltage source right here of, say, 45 volts. Now that's still pretty simple, straightforward circuit. What happens now when we add a 20 ohm resistor here, another 1 ohm resistor here? Just to make things interesting, let's stick a second voltage source of 80 volts right here. All of a sudden, that circuit is no longer simple. What is going to happen? How are the currents going to flow in this circuit?
On that 45 volts on the right side is the ground, right? Or the negative, right?
Negative, positive. Negative, positive. I mean, y'all may be a whole lot better at this than I am, but I just look at this circuit. I have no idea which way the currents are flowing. I would assume that the current here is flowing that way. What do they call that current? Since I'm going to follow the battery, well, of course, they do it backwards. I guess. I don't know. They're going to say, well, let's assume that this current flows this direction, and let's assume that current flows that direction. They call this one I1 and this one I2. And then there's a third current flowing here that they call I3. Now, I want to make this point, and I want everybody to pay attention because this is important. As long as we analyze this circuit mathematically and are careful about doing so, it doesn't matter which direction we assign any one of those currents to. As we solve the circuit, as we solve the problem, and solve for the different currents, if we apply Kirchhoff's laws correctly, and we don't make any algebraic mistakes, if we've assumed the current is going the wrong direction, then it'll show up as a negative current in our solution. And so we will find out, once we solve the problem, we will find out which way all of these currents are going. And they solve this problem in the book here. So let's go through this one step at a time. And you know what? I'm going to redraw this bigger. Try to make it a little easier to read. Did y'all notice these two resistors here and here? 1 ohm? Seriously? Why would you put a separate 1 ohm resistor here instead of just making this a 21 ohm resistor? Thank you. So these represent the internal resistance of these batteries. Yeah, I'm sure y'all, how many of you are familiar with the idea of internal resistance in a battery? Show of hands. Okay, a couple of you, but not everybody. So I'm going to stop and cover that for just a minute. When you have a battery, it uses chemical processes or some mechanism for producing a charge and a potential difference. It's a storage of charge. Well, the more readily that charge can flow out of that battery and into the circuit, the lower its internal resistance is. But the chemical processes that generate that charge and produce the potentials, they change. As the charge decreases, as the battery gets weaker, as it drains, that manifests by making it more and more difficult for the current to flow through the battery, which is represented as an increasing internal resistance of that battery. I don't know how many of you have noticed this, but you take a battery and you measure its voltage on its terminals under no load, you're going to get one reading. You attach a load to that battery and measure the voltage that it actually applies to a working circuit. It's going to be less than its open terminal voltage. That's because some of its open terminal voltage is being dropped across that internal resistance. And so, if you want to know what the internal resistance of your battery is, if you know the current that it's producing that has to flow through a circuit, and you know the voltage that it actually delivers to that circuit, then the current times the internal resistance will give you the internal voltage drop that it manifests as the difference between the terminal voltage and the open terminal voltage. Did that make any sense to anybody? If you've got a battery with an internal resistance and you start drawing a current, you attach a resistor to it. As long as no current is flowing, no voltage is dropped across that internal resistor. And all of the voltage appears across the infinite resistance between the two open terminals. But the minute you apply a resistor across those open terminals, current starts to flow through that resistor. As the current starts to flow, the voltage drop across this internal resistor starts to increase, which means the voltage at the terminal starts to decrease. Now it's going to find equilibrium where the voltage across the external resistor is the same amount of current as the voltage dropped across the internal resistor. And that's when it finds its steady state value. Of course, as the battery gets weaker, that internal resistance gets bigger, the internal voltage it drops gets bigger, And the external voltage it applies to the circuit gets smaller until the battery is considered dead or needs to be recharged. Okay? When you recharge a battery, you're reducing the internal resistance again. Until, I guess, eventually the chemicals in the battery just get too weak and the plates become too corroded or whatever, but eventually the battery won't be able, you can't recharge it because that internal resistance is more than just an abstraction of the power that's left in the battery. It actually is some physical limitations inside the battery of how much current can flow and how much potential will have to be dropped internally to push that much current. So that's why batteries don't last forever. Eventually they have to be replaced. So any of you end up working at one of these auto manufacturers or car designers where they talk about zero emission cars and electric vehicles, don't forget that eventually that all those batteries in that electric car are going to have to be put in a landfill. Because the electric cars are not zero emission. They just save up all that emission for the end of the life cycle. Yeah, I don't know how many of you have ever looked into electric cars. Oh, it can be, sure. I mean, people don't... Yeah, they can be extremely fast. And it's freaky because you don't get that that you normally expect at the starting line of the drag strip. There's no noise. It's silent. It's just, the only noise you hear is if the tires start squealing and it's gone. Don't think electric power means low power, because trains are driven by electric power. All those big diesel engines on a train, all they're for is to run the generator that recharges the batteries that push the train. How many of you have looked into the cost of replacing those batteries in that Prius?
Aren't they 7 to 8 grand?
Not anymore. Oh, not even close. You go look and you can, that $30,000 Prius that somebody paid $35,000 for, 6, 8, 10 years ago? You can buy it for a couple $1,000s now because it's going to cost you $10,000 to $12,000 to put new batteries in it. So yeah, you save lots of money at the gas pump over those 5, 6, 8 years, but when those batteries have to be replaced, you're going to be out $10,000 to $12,000. That's why you can't. It's like pulling teeth trying to call up a Toyota dealership and try to find out how much it costs for a new set of batteries for a Prius. If they think you're looking to buy a new Prius, they do not want to tell you how much it's going to cost. So it's worse than trying to get an Amway salesman to tell you that they're selling Amway. They just don't want to admit it. All right. How about we get back to the class? Okay, well, let's see. They assume, and it is just an assumption, we're going to assume that I1 is this direction. I2 is, backwards. And I3 is this direction. Yeah. And like I said, if we find in the solution that one of these currents comes up with a negative sign, then we know that we assumed the wrong direction. So it really is quite arbitrary how you decide which currents to go in which direction. Okay, everybody, put on your thinking hats and travel back in time in your Wayback Machine to the last time you took algebra. Who can tell me what we now need in order to solve for these 3 unknown currents? Three variables. What do we need to find them, to solve for them? Anybody? As a rule, and it's a hard and fast rule, for n unknown quantities, you must have n independent equations. 3 variables, we need 3 equations. And they can't just be any 3 equations. Okay, we can get our first equation very quickly. We say I3 is equal to I1 plus I2. Okay, so we've got 0 equals I3. I3 minus I1 minus I2. Or minus I1 plus I2. However you want to write it. Okay? We've got an equation. We could also write this as I1 plus I2 equals I3. Well, that's the second equation. Or we could write I1 equals I3 minus I2. That's the third equation. 3 equations, 3 unknowns. Can we solve for any one of them? We cannot. These are not independent equations. What does that mean? What do I mean when I say an independent equation? No, not really. You're on the right track. An equation is independent of another equation if it cannot be derived from that equation. See, I can start with any one of these 3 equations and algebraically derive the other 2 from it. So these are not independent equations. They are, in fact, quite dependent upon one another. So, got 3 equations, but only 1 independent equation. And it can be any one of them. It doesn't matter which. Now, since we have 3 unknown variables, we need 2 more independent equations that cannot derive from one of these. And that is where Kirchhoff's voltage laws is going to come in. We can use any closed loop to write a statement of Kirchhoff's voltage law. So if we look at this loop here, then we know that the voltage across R1 plus the voltage across, let me label these, R1, R2, R3, R4, R5. We know that the voltage on R1 plus the voltage on R2 plus the voltage on R3 have to equal 45 degrees. 45 volts. Okay, or then what's the voltage on R1? R1 is I1 times 30 ohms plus voltage on R2, which is I3 times 1 ohm plus I3 times 40 ohms minus 45 volts is equal to 0. they also point out that as long as you assume the current is going in one direction, then the voltage will either, the positive charge, so going in this direction, we're assuming I3 is going in this direction from negative to positive, which would be negative for a, how would that work? Would that be a negative voltage? Because you're well, if this is positive, if it's a positive voltage going from here to here with I3, then it would be a negative voltage going from here to here. You could do it that way, where as long as you're consistent. When the positive, they're using positive charge flow, so a positive charge going from here to here is going up in potential, so that would be plus 45 volts to go across here. Now it's going from this higher potential to a lower potential, so it's minus, what's that, I3 times 1 ohm. And then it's going to an even lower potential of minus I3 times 40 ohms. And continuing on around, it goes to an even lower potential of minus I1 times 30 ohms. And that all has to equal 0. So basically, I just took the first equation and changed the signs on everything. Point is that you have the voltage and you have the currents. You've just got to be consistent. So let's stick with that approach. And now the next thing they do is Kirchhoff's voltage law applies to any closed loop. So we could use this closed loop here, or we could use this outer closed loop here. Either one, we're going to have to be very careful about how we manage our signs. Because in this case, if we go with this outer loop, we have current flowing in one direction here and flowing in an opposite direction here. Okay? Or, if we go around this loop, then from here we're going from a lower to a higher positive potential, so that's an increase in potential. Decrease, decrease, followed by an increase, followed by a decrease and a decrease. So either way, we're going to have to be very careful about our signs, but we can choose any closed loop we want to write another independent equation. Let's go ahead and use this one. We know that from here to here is plus 80 volts. Because we've assumed the current is going in this direction. So it's then going to go to a lower voltage here, so it'll be minus I2 times 1 ohm minus I2 times 20 ohms plus 45 volts minus I3 times 1 ohm minus I3 times 40 ohms. And that brings us back to where we started. And all of that has to equal 0. Well, let's do some quick shuffling around. We got 80 plus 45 is what? Plus 125? Somebody, I haven't had enough coffee yet this morning. Somebody get out a calculator and make sure I did that right. Good? Okay. 125 minus I2 times be very careful here. I'm going to factor out I2 times 1 plus 20 minus I3 times 1 ohm minus, okay, I'm going to factor out an I3 here. 1 plus 40 ohms equals 0. So let's write it as 125 minus I2, 21, minus I3 times 41 equals 0. Okay, that should give us 3 independent equations. We have 0 equals I3 minus I2 minus I1. We have 0 equals, did I simplify this one? Okay, minus I3 times 41, let's see, equals 45 minus I3 times 41 minus I1 times 30. And finally, 0 equals 125 minus I2, 21 minus I3, 41. Did somebody see where I've made a mistake somewhere? I don't know. I just, it sounded like someone was. That's a good point. That would be I3. So, now we have 3 independent equations, equations that cannot be derived from each other. And 3 unknowns, I1, I2, and I3. And we can solve, now we can solve stepwise until we get it down to a single answer. We can start by writing I1 is equal to I3 minus I2. Okay. We could then, who has any, how would any of you proceed from here? Because at this point, it's, there are any number of ways you can proceed. And it's not always obvious what's the quickest way to get there from here. Sometimes all you can do is just plug and chug until you get to a resolution. Well, let's see here. We solved one for I1. We could solve this one for I2 by adding I2 times 21 is equal to 125 minus I3 times 41. And if we divide both sides by 21, what's 125 divided by 21? I didn't bring a calculator with me today. Somebody. 5.95 minus I3 times 41 divided by 21. 1.95. Okay. Well, now we've got a simple expression for I2. And this is the only equation we haven't used. and it doesn't involve I2. I think we just drove ourselves into a dead end. Here we've got an I1 and an I3. We have I1 as I2 and I3. Let's solve this one for I3 in terms of I2. Then what do we end up with? We end up with, we're solving for I3, so we have I3 times 41 equals 125 minus I2 times 21. So I3 becomes 125 over 41 minus I2 times 21 over 41. And that gives us, again with the calculators, somebody help. 125 over 41 will be 3 and change, right? 3.02 minus I2 times 21 over 41. 0.51. Okay. Now we have I3 in terms of I2. We have I1 in terms of I3 and I2. So we can now write I1 as 3.02 minus I2 times 0.51 minus I2. Or 3.02 minus I2 times 1 plus 0.51 So we have I1 in terms of I2. And we still have this equation that gives us I3 and I1. So we have both of our currents in terms of I2. Well,
Top equation written where I2 equals I3 minus I1, and then put those two dot equations.
exactly. Yeah, we can rewrite the first equation all in terms of a single unknown. And that will give us, well, I hope I'm not erasing something I'm about to need. Let's write, we have I1 and I3 both in terms of I2, so let's solve this equation for I2. I2 is equal to I3 minus I1. So that would be equal to 3.02 minus I2 times 0.51 minus I1, which is 3.02 minus I2 times 1.51. So that would be 3.02 minus 3.02 goes to 0. We have minus I2 times 0.51 minus I2 times 1.51 is all equal to I2. And now we would just lose all of our I2s if we solve for that. Say again? Yeah. Yeah, basically we're saying, yeah. So, and I knew I was going to end up needing those equations back. Let's see what they did in the book. We can cut to the chase. They have, going to step 5, they have 3 equations labeled 1, 2, and 3, and 3 unknowns. They solve I2 in terms of I1, and then I3 in terms of I1. And they come up with I1 equals an equation in I1. They're saying I2 equals minus I2 times 1. .51 minus 1.51, that becomes a negative 1. So, yeah, negative I2 times. That's a trivial result. We solve for I2 that I2 is equal to I2. That mathematically, that's what that's called. That's when you solve for a trivial result. They did not end up with a trivial result in the book. And they did pretty much the same thing we did. How did they avoid the trivial result? Oh, wait. Right here. Here we have I3. Here we have I3 in terms of I2. And here we have I1 in terms of I2. I2 is equal to I3 3.02 minus 0.51 I2 minus I1, which is 3.02. Aha! The algebra snuck up on me, I think. Let's take this. This is I3, right? Minus I2. I'm sorry, minus I1, which would be minus 3.02, minus a negative. So this is plus I2 times 0.51. Okay, now that is just... No, that's not times 0.51. It's plus I2 times 1.51. Now, is that a trivial result? I2, then these cancel, and we have yeah, it is. 1.51 minus 0.51 gives us I2 equals I2. Well, gentlemen, I am just a little bit irritated. And I'm especially irritated because I've erased the independent equations we started with. And I think what we need to do in this case is we would have needed to have taken two of those equations and added or subtracted them to try and get things in terms of but in their case, in the book, they went through and they solved it using their equations. And they found I1 equals I3 minus I2, which gave them, yep, that's what we had. In their case, gave them a non-trivial result of I1 equaling 0.87 amps, or equaling a negative 0.87 amps, which meant that their assumption that this was going in this direction was wrong, that in fact I1 is going the other direction. So the lesson learned here is when you've set up your equations, don't erase them. Anyway, once they solved for I1, then it was fairly easy to solve for I2 and I3. You can follow it in the book there. It's on page 535. So does anyone have any questions? That is really annoying because I must have done something wrong when I set up one of those loops. I know I did do one thing differently. They went, instead of where I did this loop and then I did this loop, and they did this loop and then they did the outer loop. But that really shouldn't have mattered. Well, anyway, questions? Any questions on the homework? Okay, well, talked about charging batteries. And now I want to cover this real quick. Yeah, I want to cover this very quickly here. We got 5 more minutes, so it shouldn't be a problem. And then Friday we'll start looking at circuits with capacitors in series and in parallel. I asked you the trick question the other day when we first started on this chapter. I asked you if a battery and a resistor, I asked you, are they in series or are they in parallel? And it was an ambiguous question. In fact, what we did come to the conclusion was that series and parallel can only describe the relationship between like items, either loads or sources. And so while you cannot put a load in either series or parallel with a source, with the battery, you can in fact put multiple batteries in both in series and in parallel. If you add them in series, then the voltages just add together. So if you put 3 1.5 volt D cells in series, one after the other, then you end up with 4.5 volts. You get more voltage. Then they will all still generate the same amount of current for the same amount of time, but you'll get a higher voltage, and you'll therefore deliver more power to the circuit, and it will come evenly from the 3 different batteries. If you put those same 3 batteries, the D cell batteries, in parallel, now you're only going to apply 1.5 volts to the circuit. But you can deliver 3 times the current, because the current will come evenly from each of the battery cells. Now, each battery will still deliver the same amount of power to the circuit, and you will still be able to deliver the same amount of power to the circuit because each battery will produce the same amount of power independently of the other 2. Your power delivered would still be 3 times what it would have been from any one of the batteries, just like when they were in series. The difference is that the power when they're in series will be a larger voltage times a smaller current. When they're in parallel, it'll be a smaller voltage times a larger current. So depending on whether you need more current or more voltage will depend on the configuration you choose for your batteries. All right. They also talk about recharging a battery. They talk about the occasion if you put 2 batteries in opposite polarity in series, where you have at that point, I'm going to go back to my office and make some coffee. The point is, if you put the batteries together with the polarity pushing against each other, the voltage, you could look at it as the voltage is going to be the difference between them. The more practical application in that would be that the larger voltage battery is going to be pushing charge into the lower voltage battery. And that's how you recharge a battery. Of course, that's presuming that the battery can be recharged. Not all batteries can because of the chemical processes involved. Any more questions? All right. See y'all Friday. Wait, we have lab tomorrow, right? No, we have lab. We had lab yesterday.
I didn't get that until 100%.